Okay, we have one last talk today, this session. This is Katherina Feng, and she comes from UC Santa Cruz.
Hi everyone, I am very happy to be back. I graduated from Penn State last year, and in the 4 years of college I got to see a lot of planets get discovered, and more of them are being characterized, as Laura has discussed. So the particular type of characterization I'm talking about today is the emission in the thermal infrared from the planets, and we're going to follow that as the planet goes around the star. So some of the emission data that we can get these days would be like so, where we can use multiple instruments to try and get as many data points as possible to get a shape of the emission. But in the future, we might expect to see, with telescopes like James Webb, all the gaps will be filled, and the precision of our data will be much better. However, the spectrum that we get is basically the result of the hemispherically. We average it over the hemisphere, and that's all we can see, when in reality, if we could resolve the planet like we have with Jupiter in the past in the near infrared, we can probably see bands, clouds, and lots of complicated structure. So these atmospheres are complex 3D structures, but we're saying that all we can get, the information on the abundances and the temperature, pressure profile, is from the emission. And so when we do retrievals on it, we want to, the information that we get, how accurate is it to the true answer? You know, it can be really precise data, but is what we retrieve from it close to what the planet actually is like? So the question I'll be investigating in grad school will be about what limits our accuracy when we're trying to analyze these data. So the first thing I'm going to do is to incorporate more freedom in our 3D models so that we can better portray planetary atmospheres. So that would mean to generate spectra of arbitrary spectral resolution and generate spectra from arbitrary compositions. And at the same time, I'm going to start exploring biases in our 1D retrieval. So you can imagine if we have a planet that's just uniform throughout, but it has a hot spot, and when we retrieve on that, is the information more biased towards the information from the hotspot, and how biased is it? And so once we figure that out, we can perform retrievals on our 3D models where we know the answers, and we can start exploring, is our accuracy better for certain wavelength ranges or certain signal-to-noise ratios? So to make a 3D model, we collaborate with people who work on the dynamics of the atmosphere. So we work with Adam Shulman from University of Arizona and Nicole Lewis. So they provide us pressure temperature profiles for a bunch of different patches on the planet for, say, 100 orbital time steps as the planet goes around the star. And because this is emission, we are basically interested in what is visible to us. So this is our sub-observer point, and what we can do is only include all the patches that are visible to us and calculate and perform radiative transfer calculations on that to generate the flux densities. So up to this point, Jonathan Fortney, my advisor, and Adam Shulman have created the SPARC model that incorporates general circulation and radiative transfer to generate 3D spectra, but SPARC is limited by its low resolution opacity grid, and it doesn't include, it won't allow for arbitrary compositions. So Caroline Morley has been working with an open source radiative transfer code called DISORT and that code is good for including any opacity grid and including different types of atmospheric compositions. So Caroline gave me one set of pressure and temperature pressures and temperatures for a 1000 Kelvin brown dwarf, And what I did is I applied that same pressure temperature profile to every single patch for my grid, and then I ran my code and added and summed up all the fluxes, and I compared, and they seem to match pretty well. And the discrepancy, you can see there are discrepancies, but that also highlights an advantage of our code now, because if I run my code again with the opacity grid that she had run with, then you can imagine that the disagreement would be much smaller. And so after that little bit of sanity check, I used Jonathan's run with Spark on data on his model for WASP-43b, and the GCM, the general circulation model, was provided by Tiffany Kataria at the University of Arizona. And so what I did is I ran the code with the same pressures and temperatures that Jonathan ran Spark with, and then I smoothed my data to fit the resolution that Spark resulted in, and you can see that they match pretty well. That's a good sign. And because we're interested only in the patches that are visible to us, we can tell the code where the sub-observer point is, and in that we can include information about the inclination and then throw away all the patches that we can't see for a given inclination. And so I ran the same code for 3 different inclinations. One is for edge on, 90 degrees, and one is for the inclination of WASP-43, which is 82, and one for an extreme case of 45 degrees. So the white is basically right on top of the red curve, unless you zoom in a lot. So it's safe to say that it's okay to assume edge on for our modeling, but it's still good that we have the opportunity to include different values of inclination. And while it's nice to see the flux density as a function of wavelength, I thought it would be nice to also see what it's doing on the actual planet. And so here is the case for 90 degrees, and this is only for fluxes at 1.43 microns. I just chose that randomly. And this is for the case when it's at 82 degrees inclination, and then here we have when it's at 45 degrees. So it's interesting to see how that changes. So we can do this kind of analysis for any of the wavelengths that we run our code on, and we can also do it for all the different phases that we have pressure temperature profiles for. So what you can hopefully garner from this is that these atmospheres are really complex 3D structures, but when we're trying to retrieve information about the compositions and the pressure temperature structure, we're treating it as a 1D retrieval. And so what I want to do next then is to start testing for biases in our 1D retrievals by simply trying the case where it's just a planet with just a night side and a day side, one pressure profile for the day side and one for the night side, where the night side is due to just the internal heat flux of 350 Kelvin, and there's no redistribution between the day and the night side. So let's say we're observing this planet, but what we observe is actually the averaged result of these two pressure temperature profiles, and we want to retrieve on that to see, is it more biased towards the information from the day side, and if so, how much? So I calculated the emerging flux at the top of the day side and at the top of the night side, and I averaged them, and then I divided by the flux of the star and added random noise to simulate data, and so the data in white is what we will be retrieving on, and this is work I've started with Mike Lang. So on the top is our retrieval for just our standard day and night side. We bin the data to imitate the Hubble WFC3 data. And on the bottom, I tried a trial where I made the resolution higher just to see what effect that has on a retrieval. And you can see that the result is indeed biased towards the day side. And when I try and change the signal to noise ratio, so if I say that the data has smaller error bars. You can see if the retrieval is any different, and it is slightly different. So there's a lot of room for exploration in this case. And what I thought was interesting is that the median for the retrieval, so for all the parameters that could fit the possible data, the shape of the pressure temperature profile is similar to the night side, even though it is biased towards the day side. And so in my years through grad school, I'm going to continue working on the 3D models to make them better, to make them emulate real atmospheres. And I will continue my exploration of the biases in our 1D retrievals and eventually apply those retrieval techniques on our 3D models, which we know the answers for. We know what the compositions are, and then we can start exploring for what wavelength ranges is our retrieved quantities better, and or for what signal-to-noise ratios.
Questions?
So how does atmospheric circulation affect your retrieval? Do you have to make some pre-assumptions, or is that part of the retrieval process?
I don't think it affects the retrieval. But what do you mean? Do you mean
Like for instance, like if you have like shocks at different layers, how does that process affect your and if there's any like chemical mixing or things like that, is that going to be a part of the code, or is that a pre-assumption from like your planning?
Yeah, so I think what we want to do is, I think that'll come in the part of the models and what comes out of the models, and the retrieval shouldn't be able to know what's going on in the planet, so we want to see if the retrieval will be able to detect any signs of complicated things like jets or clouds.
Could you talk a bit about gains that you get from, in what cases we should do 3D versus should we stick to 1D in some cases?
So from what I understand is that all retrievals we do are one-dimensional. But what we're trying to do is, by having this 3D model, it can simulate a real atmosphere better. So when we retrieve on that, it would be more like retrieving on a real planet, because the real planet is like a 3D structure.
Following up with this question, for example, if your 3D model doesn't include feature like cloud or jet or the uniformable surface of the planet, how do you expect it can retrieve precisely the atmospheric properties of the planet? Do you have a plan of including these features in the future model?
Yeah, absolutely. So right now we've been working with cloud-free models, but eventually we'll start incorporating clouds and just start doing test cases of more and more complicated 3D models to see how the retrieval performs.
Anything else? Okay, thanks.